Okay, so reading the handout, Galileo's inclined plane experiment. Now, this particular handout, you'll notice the way at the bottom there's a date. I printed this out in 2003 for a class, so I've been going through this a lot of years. So what this is this is a write-up from a university from a bunch of students who basically replicated or redid Galileo's inclined plane experiment just to sort of get an understanding of how it worked. And we're going to be doing an even sort of more basic sort of one in the next couple days. So it says, using equipment that we might call simple or even rudimentary, Galileo revolutionized basic scientific principles which were posited by Aristotle and held firmly by scholars of the High Middle Ages and Renaissance. Anybody want to guess at the word positive? Put forward? Yeah, it's exactly what it is, right? So Aristotle put forward these scientific principles, and they were believed for basically 2,000 years. Only one problem, Aristotle was 100% wrong. One of his most important experiments, this is Galileo now, was the inclined plane experiment. Galileo used his inclined plane, a simple board with a groove down, which he rolled a small metal ball to examine Aristotelian ideas about motion. Galileo's inclined plane experiment radically changed these ideas by concentrating on acceleration, a stage of motion ignored by Aristotle and most of his followers. Come along there, Jason? We decided to replicate Galileo's inclined plane experiment because it was so fundamental to two concepts of motion in Galileo's time. We based our experiment on Galileo's own description of the inclined plane in his book, Discourses on Two New Sciences, published in 1638. So this is Galileo's words. A piece of wooden molding or scantling about 12 cubits or 7 meters long, half a cubit or 30 centimeters wide, and 3 finger breadths about 5 centimeters thick was taken. On its edge was cut a channel a little more than 1 finger in breadth, and having made this groove very straight, smooth, and polished, and having lined it with parchment, also as smooth and polished as possible, we rolled along a hard, smooth, and very round bronze ball. So Galileo's words again. So they took a piece of board, and you saw it in the video, and you're going to see it again. They took a piece of board and they put a groove down it, much like our ramps as well. His was a little bit sort of nicer, kind of rough, but basically that idea. So now, the students at Rice University, these are their words again. Our own construction entailed planing a 45-degree angle on each edge, each on two 16-foot 2x4s, which when nailed together formed a groove. We sanded and oiled the groove to create a low friction effect like Galileo's parchment. Instead of a small bronze ball, we used a 3/4 inch steel ball. We added a metal piece to the end of the inclined plane against which the ball struck at the end of each run to make our timing precise. Click here for a more detailed description of our inclined plane. So they took two 2x4s and they cut sort of the edge off, cut the corner off, put them together so that they had sort of like a V-shaped channel. And then they sanded it down, and then they used a ball bearing. We also replicated Galileo's apparatus for timing the inclined plane experiment. Galileo describes his water clock in Discourses on Two New Sciences. So, Galileo's words again. For the measurement of time, we employed a large vessel of water placed in an elevated position. To the bottom of the vessel was soldered a pipe of small diameter, giving a thin jet of water, which we collected in a small glass during the time of each descent. The water thus collected was weighed after each descent on a very accurate balance, and the difference in ratios of those weights gave us the differences in ratios of the time. So in Galileo's time, in 1638, he did not have an iPhone, he did not have a stopwatch. He might have had a clock, but it would certainly not have measured seconds. He might have had one of those things you flip upside down, the hourglass kind of thing, right? But how accurate would you be able to measure time with that? Not very accurate. So he was faced with this problem of how to measure the time. So he came upon this ingenious idea, and he used the amount of water as time. So it's not measured in seconds. In fact, the time is actually measured in grams of water. Okay, so obviously the more time that elapsed, the more water you've got, right? So if you got a lot of time, you got a lot of water, right? And then he just simply looked at the ratios of times. We have twice as much water, 3 times as much water, and that's how he worked out the times. We're going to do it. We're going to use stopwatches, but that's how Galileo did. Back to the Rice University work. Do you follow along there, Annika? Pardon me? Oh, why didn't you say, hey, Mr. Bennett, I need a sheet? How did I get a sheet? You didn't. Okay, so again, the students from Rice University. Our water consists of a plastic bucket with a small hole drilled in the bottom, into which we place a length of plastic tubing. When filled with water, the bucket emitted a thin stream of water through the plastic tubing. We control the flow of water by clamping the tubing with a small metal tap. We marked our inclined plane at 1/4, 1/2, and 3/4 of its length. Starting with the full length of the plane, we rolled the ball 20 times down each length, timing each trowel with our water clock. Like Galileo, we weighed the water from each trowel so as to determine the ratio of times for each length. So they marked it in what ratio? They marked it at 1/4, 1/2, and 3/4. And they timed it with their water. And then they weighed the water, and then they figured out what was the ratio of those amounts of water. Our experiment proved that Galileo could have attained the accuracy which he claimed for his experiment. Our findings also point clearly to the concept of acceleration. The ball travels down 1/4 of the plane in half the time it takes to traverse the entire plane. Aristotle would have posited, of course, that the ball's timing would be directly proportional to the distance traveled. Aristotle would have said, twice as far, twice as much time. Never bothered to do an experiment, and people disbelieved him for 2,000 years. I often wonder how advanced our civilization would be at this point if we hadn't just believed him for 2,000 years and actually tried an experiment out to see if it worked. Probably someone did, but no one sort of wanted to go against sort of that establishment, and they may have been probably killed for such crazy thoughts. Andrew Irving has created graphs which clarify Galileo's discovery that the ratio of the distance traversed by the ball is proportional to the ratio of the squares of the time. So it deals with acceleration. And if you look at this picture here, okay, which you guys have, and I'm just going to explain this here, and then we'll watch the video again. I'm going to zoom in a bit here. This table of values is important because this table of values here, you're going to be duplicating it, you're going to be copying it in the future experiment. Annika, have you got this one? Where is it? Can you get it out so that you can follow along so that when we do the experiment, you'll know what's going on? Thank you. You will notice then in the picture, how far does the ball go in the first second? From there to there, how far does it go? 0.5 meters. A mere 0.5 meters. And then where is it at the end of the second second? Where is it at the end of the second second? It's at 2 meters. How far has it traveled in the second second? 1.5 meters, right? You are right. 2 minus 0.5. It's traveled considerably more. How come? Because it's speeding up. And where is it at the end of the third second? 4.5. How far has it traveled in the third second? 2.5. So it's gone 0.5 meter, then it's gone 1.5, and then it's gone 2.5. How far did it go on the next one? 3.5, and then 4.5 meters. It goes farther and farther each time, just like when we looked at acceleration with the yellow car kind of thing, right? Okay, now let's look at the table down below here. Okay, now watch carefully because again, you're going to have to be filling this in on your own. So when you say, I don't understand this, I'm going to ask you, did you listen that day that I was talking about Galileo and the little table of values? Okay, so down the left-hand side, what are these things here? Interval numbers. So interval number, you can number them if you want. 1, 2, 3, 4, 5. Interval number. What is the time at the start of the first interval? 0. What is the time at the end of the interval? 1. What's the start time of the second interval? 1, and the end is 2. And you'll notice that these numbers do this. You see that? Because the end of the previous interval is the start of the next one, right? Okay. How long is each interval? It doesn't show it here, but how long is each interval? How many seconds? 1 second each, right? Okay, position at the start of the interval. Where does it start at? It starts at 0. At the end of the first interval, it's at 0.5, right here. It's at 0.5, which means that at the start of the next one, it's at 0.5. Does that make sense? Give me the nod of understanding. Okay, good. And where does it end up at the end of that interval? At the position 2, which is, of course, exactly where it starts the next one. You see that little pattern there? Right? Because at the end of one interval, Colin, you're not paying attention, and later I'm going to have to re-explain it to you. Listen now. No, you're talking to him. I can see it. At the end of one interval is the start of the next. Okay. How did they find out the distance traveled? This is displacement that we've covered a few times. Final minus initial, right? So 0.5 minus 0 is 0.5. 2 minus 5 is 1.5. 4.5 minus 2 is 2.5. 8 minus 4.5, 3.5, right? You'll see that the distance traveled is increasing, right, each time. How come? Because it's going faster. Now, average velocity during the interval. Write a little formula above it. Go V bar equals D over T. Okay? How far did it travel in the first interval? How far did it travel in the first interval? 0.5. How long did it take? 1 second. So it went 0.5 meters in 1 second, which gives us a average velocity of 0.5. How far did it go in the second interval? 1.5. 2 minus 0.5 is 1.5. And how long is each interval? 1 second. So 1.5 divided by 1 is 1.5. You'll see that the speed is doing what? Going up by 1 meter per second. The average is going up by 1 meter per second every second. How come? Because it's speeding up. Okay, here's the even harder part. Focus here with me. What is the velocity, the instantaneous velocity at the start of the interval? How fast is it going right at the very start of the whole thing? 0. It's at rest. 0. Now, listen carefully here. If it starts at 0 and it averages 0.5, what does it have to be going at the end of the interval so that it averages 0.5? It has to be going 1. 0.5 is exactly in the middle of 0 and what? 1. Right? This is exactly in the middle. This value here, we don't know just yet. I mean, you can see it, but that's what I'm trying to find out, right? Okay, so the average of 0 and 1 is 0.5. Now, if you're going 1 meter per second right here, at this point right here, you're going 1 meter per second. At the end of the first interval, you're going 1 meter per second. How fast are you going at the start of interval 2? 1 meter per second, right? The end of the first interval is the start of the second. So again, you see this pattern, right? You see that? Okay, so now, whoopsie, let's go back to our average velocity. If I started at 1 meter per second at the start of that interval, and I averaged 1.5, what do I have to be going at the end? 2. 0.5 is exactly in the middle of 1 and 2, right? What's the average of 1 and 2? 1.5. And if I'm going 2 meters per second at the end of that interval, then what does my next interval start at? 2 meters per second. And if my average is 2.5 and I started at 2, then I have to end up at 3. And if I end at 3, then I have to start the next one at 3. And if I start at 3 and I average 3.5, how fast am I going at the end? 4. And if I end the interval at 4, how fast am I going at the start of the next interval? 4. And if I start at 4 and I average 4.5, then I end at 5. And so my speed is going up. My instantaneous speed is going up by 1 meter per second every second, which is known as an average acceleration of 1. The acceleration is 1 meter per second squared. How come? Because the velocity is going up by 1 each time. Okay, now, this is in a perfect, maintained, frictionless, perfectly timed situation. Is Galileo going to come up without this kind of stuff? Is he going to come up with perfectly 1.0? Not even close. Are you going to come up with perfectly 1.0? No. In fact, you're going to come up with a big mess. It happens every year. Okay? But you have a better understanding of how it works. and you have a pretty good appreciation of just how patient Galileo was. Okay? So this is a velocity time graph, which shows the velocity, right? Okay, so what you do is you simply read off the graph the velocities. What is the velocity at 0 seconds? 1. Right here, see, Riley? At 0 seconds, it's 1. What is the velocity at 2 seconds? 2. What is the velocity at 5 seconds? Looks like 3.5. Are you guys watching? Savannah, you packed up. What is the velocity at 10 seconds? 6. Okay, so all you've done there is read off the graph. Now the acceleration is the change in the velocities. Now you'll notice that it's kind of offset. It doesn't match up. That's supposed to be like that. Okay, so how much did the velocity change? It went from 1 to 2. So the acceleration is 2 minus 1. A time went from 0 to 2, so 2 minus 0. So it's 1 over 2, or 0.5. The acceleration is 0.5. I'll zoom in to give myself a little bit more room to write. Okay, then the next acceleration. It ended at 3.5, it started at 2. So it's going to be 3.5 minus 2. How much time elapsed? From 2 seconds to 5 seconds? 5 minus 2, or 3. 3.5 to minus 2 is 1.5 over 3, which is 0.5. Again, how much did the velocity change? It goes from 3.5 to 6. 6 minus 3.5 all over 10 minus 5, which is 2.5 over 5, which, surprise, surprise, 0.5 meters per second squared. How come the accelerations are all the same? Because it's what kind of graph? Straight line. In fact, what is the slope of the line? 0.5. 0.5 meters per second, or 0.5 meters per second squared. We did slopes back in Unit 1. The acceleration is the slope of the velocity time graph. Now, on the second page, is it a straight line? It is not. Are you going to get all these same accelerations? No, you are not. So please have that done tomorrow, if you are not already done. We're not actually looking for tangents here. That's a good point. We're actually just looking for average acceleration. So over that interval. So all you do is just read off the velocities off the graph and then subtract and find the accelerations. Okay, I will leave you with that. Please have that for tomorrow. We'll check that first, and then we're moving on.